Today I'd like to get you ready for your thermal test. So the big thing you want to keep in mind is when we're looking at a box full of gas, that the gas particles are in random motion, random in terms of speed and direction. When we look at a distribution of the speeds, we get graphs that kind of look like bell curves, but shifted a little bit to the right. You can see this is for radon at 3 different temperatures, and you can see that the higher the temperature, the greater the distribution of speeds, and you can see the smaller the temperature, the more compact the distribution of speeds. You can also see the most probable speeds are where the peak occurs. Okay, some of the big terminology from the unit are temperature, pressure, volume, and number of particles. Remember, temperature should be equated with kinetic energy of the particles. Pressure should be related to the collisions that the particles make with themselves or with the walls of their container. Volume is how much space they have, and the number of particles is often given in moles. Okay, I wanted to make sure you remembered how to get the speed of the most probable or the average particle. Okay, so if you're looking at the most probable, you use this formula for kinetic energy, and then plug your kinetic energy into your main kinetic energy equation. If you're looking for the average speed, you would use 3/2 kT. Remember, the K is Boltzmann's constant. And then again, you solve for speed. Make sure you turn your masses from atomic mass units into kilograms. Expect to get speeds in the hundreds or even thousands of miles per hour. Okay, I want to make sure you remember some formulas for the full container. Okay, so if we're looking at all of the molecules, because these formulas we were just focusing on a single molecule or particle. Okay, so if we're looking at the full container, we have PV equals nRT. Make sure you work in the right units. That's pascals, meters cubed, Kelvin. Again, the R is your ideal gas constant, and the N is your number of moles. This formula tells you the total change in energy of the particles inside the box. Okay, so when the temperature changes, the internal energy changes, and that internal energy is kinetic. If you have a sealed container and things change about the gas inside this sealed container, you can use your combined gas law. Make sure you're working Kelvin, but then you can work in any other unit you want for the pressure and the volumes. Okay, when you have a piston and you're looking at how much work goes into or out of your gas, you want to remember the formula work equals pressure times change in volume. Okay, whenever you decrease the volume, you compress the gas. Work is going into the gas. And if the gas expands, it pushes the piston up. That's going to be work coming out of the gas. Remember that you can also relate the pressure of the gas to the force by using pressure equals force over area. So if we knew the pressure in here and the area of the piston that's being affected by the gas, we can find out how much force it's applying to that piston. Okay, remember the fire syringe where we compressed our piston really quickly. We get a big increase in temperature, we get an increase in pressure, and we could actually cause the object to light. Okay, remember, in addition to work, we could also have heat going into the gas. That's going to happen if the outside is warmer than the inside. We could have heat come out of the gas, and that is when the outside is cooler than inside. Okay, so you have work that can go in, and you have heat that can go in or out. Okay, and they are related by the first law of thermodynamics. which says the change in kinetic energy or the change in internal energy, we can use them interchangeably, is equal to the amount of heat that goes in plus the amount of work that goes in. Remember to make sure you have your signs right, so sometimes the heat will come out, make it negative. Sometimes the system will expand, so you make your work negative. This will be negative if the temperature drops, and that'll be positive if the temperature rises. Okay, so we create a chart with all of these different scenarios, and this should already be in your notebook, but take a moment to look it over again. We learned how your internal combustion engine works. I'm not going to test you on the specifics of this. I just hope you appreciate the engineering that goes into this process to get useful work out of a burning fuel, in this case gasoline. Okay, remember it had 4 different parts to the cycle. We had the intake, we had the compression, we had the power stroke, and we had the exhaust. Remember that PV diagrams are used to analyze how good the engine actually is. So you make a plot of pressure versus volume as it goes through its different stages. From those PV diagrams, you can calculate things like how much work, how much heat, and more importantly, what is the efficiency of my engine. Okay, so I wanted to remind you of how you went through this process. So this is not a complete cycle, but just a single stage. And you can start by using your PV equals nRT to get the temperature at the 2 extremes of your process. Okay, so you read the pressure and volume from the graph, you need to know how many moles of gas are in your container, and you solve for temperature at both spots. Once you have the temperatures, you can find the change in internal energy by looking at the change in temperature. You could then use work equals P delta V. You have the pressure about 300 kilopascals. Make sure you put it in regular pascals. And you have your change in volume from about 0.1 to 0.4, so about 0.3 cubic meters. Once you have all of these things, you could then plug your work in here. Again, it would be negative because it's expanding. You'd plug your change in internal energy in for the kinetic energy change, and you'd solve for Q. If your Q comes out positive, that means heat went in, and if your Q comes out negative, that means heat left your system. Remember, there are 4 different common transitions. Obviously, there's lots more, but these are easy ones to deal with. We have isobaric, constant pressure. We have isovolumetric, that is a constant volume. We have isothermal, that's one that takes place at a constant temperature. And we have adiabatic, which is one where no heat enters or leaves the system. Okay, with the isovolumetric, since there's no change in volume, the work is 0. With the isothermal, there's no change in temperature, so that means the internal energy change is 0. And finally, the adiabatic, your heat is 0. Okay, on that one, you have no heat entering or exiting the system. So for that process alone, you're going to have no change in entropy, because entropy was heat divided by temperature. We looked at the engine schematically, and we saw that we could break it down into 3 energy flows. Energy comes out of your hot source, your fuel that's burning and creating heat. Some of that heat gets dumped into the cold reservoir, that's your coolant. And then the important stuff is the work that comes out. When you're finding your efficiency, you want to take the work that comes out and divide by the heat that you paid for. Remember, to see how much the efficiency of the engine can possibly be, we need to deal with entropy. So we learned 5 different ways to increase entropy: adding particles, adding volume, raising the temperature, breaking up a molecule, or changing the shape of an object. Okay, and the reason why entropy was important is it has been found that the best engine we could ever create would be one where the delta S net is 0. So you look at the delta S for the hot, the delta S for the cold. You make sure they are equal but opposite. So this is going to be a negative delta S because we are losing heat. This one's going to be a positive delta S because we're adding heat to our reservoir. And for that process, if these two delta S's are equal and opposite, we will have no change in entropy to our entire system, which is the best that we can hope for. So this will be the most efficient engine. Okay, sometimes you will have a complete cycle and you want to find all of your things for the entire cycle. Then you take all of the heats that go in, they would be your QHs. All the heats that come out, they would be your QCs. You take the work that comes out and the work that goes in, and you find your net work. And then you put that all onto your engine schematic to find your efficiency. Okay, so here we have a bunch of different formulas. We kind of already went through them all, but it might be helpful to kind of consolidate not just these, but all the ones that we had in this slideshow onto a single paper so that you have a formula sheet that you can reference. The final thing we had is we learned about conduction, and we saw how conduction was controlled by chain reaction, where the faster molecules hit their neighbors and speed them up, and the energy transfers from the hot to the cold. We learned our formula for conduction. This side is the rate of transfer through a barrier. This is based on what the barrier is made out of. How much area is there for the heat to go through the barrier? The difference between the temperature on the two sides of the barrier, and finally the thickness of the barrier. So these are all the ideas you want to make sure that you understand going into your test that's coming up very soon.